Welcome back to the Deep Dive. Today, we are getting into a really foundational architectural shift that is, I think, completely changing how businesses operate.
He really is.
So if you're an enterprise architect, an engineering lead, or, just tracking where AI is headed next, this deep dive is definitely for you.
Yeah, for the last few years, AI in the enterprise has been mostly a research assistant.
Super smart librarian.
Exactly, a super smart librarian. It would search through mountains of documents, summarize data, answer complex questions using things like retrieval augmented generation or array.
Right, so it grounded the models in your internal knowledge.
It did. But the critical point is that the human was always in charge of the final outcome.
The systems were totally passive. You'd ask a question, you would spit out an answer, and then you, the human, decided what to do. You'd write the email, approve the transaction, update the database.
But that's changing.
Our sources confirm we are deep in the middle of a massive architectural pivot. We're moving to what are called agentic systems AI, built not just to inform, but to actually execute.
And that's the leap. It's the leap from passive information retrieval to autonomous tool-mediated action.
So we're moving past just asking, what's the policy for processing claims?
And we're moving toward telling the system, achieve this business outcome. Process, approve, and finalize this claim. And by the way, navigate any obstacles you run into.
And that requires a total architectural redesign. So our mission today is to really unpack the rigorous systems engineering needed for this shift.
Yeah, because the old stateless query response model just can't do it. It can't support agents that are now performing state changes.
You mean actually altering data, moving money, adjusting real-world operations?
Precisely. The new system has to be stateful, it has to be durable, and, maybe most importantly, verifiable.
And that last word, verifiability, that gets to the central tension here, doesn't it?
It's the whole ballgame, the inherent stochasticity of the models.
The unpredictability.
Exactly. The large language models at the core are probabilistic. They can be unpredictable. But the enterprise systems they touch have to be deterministic, secure, and auditable.
So bridging that gap between the fuzzy model and the rigid system.
That's what this entire architecture is designed to solve.
So the big conceptual breakthrough is that the focus isn't on surfacing information for a human anymore.
No, it's on achieving a defined, measurable state change in the digital or even the physical world.
The model is no longer the application.
Absolutely not. The model is just the reasoning engine. And that engine has to be plugged into a much broader, highly controlled loop.
A control loop.
A control loop that ensures autonomy can exist without rigorous, externally enforced control. Think of the LLM as a brilliant, but maybe slightly wildcard employee who needs strict programmatic oversight on every single thing they're trying to do.
Okay, so let's unpack that. Let's really get into the architectural differences between the old retrieval world and this new action world. I mean, it's got to be more than just adding tool calling to a prompt.
Right. Oh, it's a foundational redesign. The contrast is, it's profound. Let's look at the old retrieval-centric architecture. Its core function was just to surface context.
To help a human make a decision.
Exactly. So systemically, it only needed read-only access to knowledge bases, vector stores, that kind of thing. Its security profile was actually pretty straightforward.
You just couldn't change anything.
It couldn't alter the environment by design, but this new action-oriented agentic architecture completely flips that on its head.
The function and the security profile.
Everything. The core function shifts from grounding context to decomposing goals and executing state changes with tools.
Which means?
It means it needs read-write access to your most critical systems. APIs, financial databases, the core systems of record.
And that simple shift, just from read-only to read-write, that must introduce a whole new world of complexity for security and governance.
It's an entirely new dimension of risk.
Okay, what about the execution context? In the RAG world, I ask a question, the server processes it, and then it forgets it. It's stateless.
Or maybe session-based, for a little short-term memory. But agents have to perform these complex, multi-step tasks.
Right.
So the system must support stateful, long-horizon, durable workflows. Think about an agent managing a supply chain order. That might take 3 weeks and involve 20 different API calls, maybe even some human handoffs.
So if the system crashes on day 5,
the agent has to be able to pick up exactly where it left off. It needs to maintain all of its context, its transaction history, and that demands a level of durability and state persistence that a simple stateless query system just can't even dream of handling.
and where we used to rely on clever prompt engineering for control.
Right, just telling the model what to do.
The action-oriented system needs something much more robust on the governance side.
It demands programmatic rigor. The control mechanism shifts from just prompt engineering to needing robust external things like programmatic guardrails, verifiable critics, and critically tamper-evident transaction logs.
You can't just trust the model to be nice.
You have to enforce its compliance through code. There's no other way.
I think for the business side, the biggest change is how you measure success. You're not measuring semantic relevance anymore, like how good did that answer sound?
That metric is gone. Now you measure task completion rate. You measure the achievement of measurable business outcomes.
Did the system actually process the invoice correctly and in compliance with regulations?
Exactly. Did it correctly update the customer record across 3 different legacy systems without errors? We're talking about agentic workflows now. These are dynamic, resilient sequences of jobs that interpret high-level goals. They don't just follow brittle, fixed scripts.
So if an API fails,
If the payment gateway API fails, the agent has to be able to reason and then select an alternative tool or strategy to still achieve the goal. And that's precisely why we need this durable, closed-loop control system.
that real-time decision-making, refining its approach based on feedback. That leads us right to the heart of this architecture, doesn't it? The adaptive engine, this self-optimizing closed-loop control system.
The closed loop is mandatory. You can't have reliability or adaptive behavior without it. It's all defined by this foundational cycle. Sense, plan, act, learn.
And this is what moves the agent from being a passive instruction follower.
To an active, rational actor that is constantly managing its environment to move it toward a defined goal state.
Okay, let's start with sense. It sounds like just pulling in data, but the sources are clear. It's much more than simple ingestion.
It goes way beyond that. The sensing phase is about intelligent parsing and critical context enrichment.
So it's not just reading a data stream.
No. Raw inputs, whether they're API responses or telemetry from industrial equipment, they have to be transformed into actionable intelligence that actually means something for the agent's goal.
Can you give an example?
Sure, it's not enough for the agent to know the temperature is 80 degrees. The agent needs to know that 80 degrees is 10 degrees above the prescribed operating rule for the specific machine, and that constitutes an anomaly that requires action.
So sensing is really about interpreting the data against the established rules of the environment.
Exactly. It identifies anomalies, it assesses the current conditions against predefined business rules, and it structures that complex reality into a set of discrete facts that the planning agent can then efficiently reason over. It's about the meaning and the relevance of the data.
Okay, so once it has the lay of the land, it moves to plan. This is where the model's core reasoning really kicks in.
This is the decomposition phase. The big high-level goal, let's say deploy the new software patch securely, gets broken down into a sequence of operational subtasks.
Like stage the environment, run diagnostics.
Notify stakeholders, execute deployment, verify the logs. The planning agent reasons about these steps. It identifies which specialized tools or even other executor agents are needed for each step, and it puts them in a coherent order.
And we have to really emphasize the separation of duties here. This is critical.
It's absolutely vital. The planning agent reasons about the steps and identifies the tools, but it maintains a very clear firewall. It does not interact with the environment directly.
It just produces a plan.
It produces a structured, detailed, verifiable plan, often in a format like JSON or XML, which is then handed off. This separation is fundamental for security and for auditing.
Which brings us to the act phase. This is the moment where theory becomes reality and the state change actually happens.
The act phase is the execution layer. It takes those discrete operations from the plan and executes them using secure tool connectors. And this is where governance becomes mandatory.
The guardrails.
Every single action has to be contained by explicit security guardrails that enforce the least privilege principle. Before a change gets written to a system of record, the parameters have to be validated against policy.
So if the plan says delete a user account,
The execution logic has to first verify that the agent has the current authority to do that and that the account meets all the criteria for deletion. It's a final check.
and finally, learn. This is how the system gets better over time.
The learn phase is really about system optimization. The outcome of the act, step success, partial success, failure, is checked against the original success criteria. This result, along with the entire thought process, gets stored in a layered memory structure.
And that informs future decisions.
Exactly. It creates the foundation for long-term reliability.
Could you elaborate a bit on those memory types? The layering sounds important.
It is. We have to distinguish between short-term episodic memory and long-term semantic memory.
Okay.
Think of episodic memory as the transcript of a single complex task. It stores the traces, the specific inputs, tool failures, successful API calls, but only for one single ongoing workflow.
So that's for debugging and auditing that specific run.
Right, and then you have semantic memory, which is the institutional knowledge, the accumulated wisdom.
The big picture.
Exactly. Semantic memory stores the accumulated business rules, historical patterns of what worked and what didn't, updated domain knowledge, common error resolution playbooks. This long-term knowledge base is then used to ground the agent's reasoning across all future unrelated sessions.
So the system actually learns from its mistakes and successes.
And the plan phase becomes progressively more efficient and reliable over time.
That distinction between the transient memory for one job and the long-term governance for all jobs, that brings us directly to the architectural need to separate responsibilities.
It does.
You can't just lump the LLM, the rules, and the execution logic into one big service. The sources are pretty clear. You need distinct planes of responsibility: control, data, and trust.
This separation is foundational. You have to do it for enterprise-level scaling, for security, for governance. If you don't separate these concerns, a failure in one area, say a bad policy update, could cascade into a system-wide security breach or a total loss of control.
So each plane has a very distinct, non-overlapping job.
A clear mandate? Yes.
Let's start at the highest level then, the control plane. This sounds like the central command for all policy and governance.
The control plane is the high-level governance layer. It defines the rules of engagement for every single agent in the ecosystem. You can think of it as the system's chief compliance officer.
So it handles things like multi-tenancy.
Yes, it manages the multi-tenant isolation layer, which is crucial if you have different business units, finance, HR, operations running agents on the same platform. It ensures there's clear programmatic separation between them.
And this is where an agent gets its identity.
This is where it houses the role-based access control, the RBAC engine. Every agent gets a unique, verifiable identity when it's created. And that identity is the token that unlocks all of its permissions later on.
And it governs through something called policy as code.
Mm.
Why is that principle so important here?
Because governance rules can't be vague. They can't be subject to interpretation. They have to be defined centrally in an executable format and then enforced across all agent interactions.
So you're coding the rules directly.
Exactly. These policies cover things like no financial transaction over $50,000 without a mandatory human-in-the-loop trigger, or only agents with the data manager role are allowed to delete data in the production environment. The control plane ensures these rules are checked and enforced universally.
And the ultimate safety net, the kill switch, lives here too.
Absolutely. The control plane manages resource quotas to stop cost overruns, and most importantly, it provides the mandatory kill switch mechanisms. If an agent gets stuck in some uncontrolled recursive loop or there's a sudden suspicious spike in high-risk actions,
The control plane shuts it all down.
it's the single point responsible for instantly halting all autonomous activity across the entire agent swarm.
Okay, moving down a layer, we have the data plane. So if control is the policy setter, the data plane is where the work actually gets done.
That's a good way to put it. The data plane handles the actual execution environment. It contains the agent runtime, the workflow engine, and the secure tool connector framework that lets agents talk to external APIs.
And its biggest challenge is managing context for those long-running tasks.
Right. This is where those memory types we talked about come into play. The persistence mechanism has to manage the short-term episodic memory and the long-term semantic memory.
But you mentioned something else for really complex multi-day activities.
Yes. For something like an agent working on a large-scale software refactoring project, you need a work tree state.
And what does that work tree state specifically hold on to?
It's like a persistent virtual desk for the agent. It maintains a consistent workspace. This includes intermediate results, specific config files, the status of partially completed documents, resource handles, all of it.
So if the agent crashes or is paused for human review,
It can resume its complex work exactly where it left off. It prevents the loss of context that would force it to restart a very time-consuming reasoning process from scratch.
Okay, and finally, the most critical and really the most novel component here, designed specifically to deal with AI's unpredictability, the trust plane. Why do we need a dedicated trust plane if the control plane is already handling policy?
That is an excellent question. And it gets to the core of separating concerns between definition and verification. The control plane defines the rules. The trust plane is the dedicated, independent enforcement mechanism that verifies compliance in real time. It's the independent auditor.
So why separate them? Why not have one plane do both?
Performance and integrity. You want your high-level policy engine, the control plane, to scale independently from your high-precision, low-latency verification engine in the trust plane.
And the trust plane works through something called interposition.
Right. It literally inserts verifiers and critics between the planning agent's reasoning output and the final tool invocation in the act phase.
So the agent comes up with a plan, proposes an action, and the trust plane gives it a mandatory programmatic security check before it's allowed to touch any real enterprise system.
Precisely. Every proposed action, whether it's updating a record or calling a service, is scrutinized against safety invariance and compliance rules in less than a millisecond.
And if it violates a rule,
If the agent's plan suggests, say, accessing a production database without the required authorization token, the trust plane blocks the action immediately and triggers an escalation. It's the final, dedicated gatekeeper for enterprise safety.
and this is where accountability comes from.
It is the backbone of accountability. It's solely responsible for generating and maintaining the tamper-evident audit trail, which we'll get into more later. It cryptographically links every decision, every policy check, and every state change to a specific agent identity, ensuring you can't deny what happened.
This three-plane structure really drives home the need for serious systems engineering. We're moving way beyond just throwing a single monolithic LLM at a business problem.
We have to.
And that need for specialization brings us to cognitive engineering. Why do monolithic agents fail in this kind of enterprise context?
They fail for two main reasons, really: context overflow and a lack of reasoning depth for long horizon planning.
So you just overwhelm the model.
You do. If you ask one giant model to manage a global software deployment, it's going to exceed its context window pretty quickly. It'll confuse its goals, it'll become unreliable. The sheer complexity of an enterprise task space is just too big for one entity to manage efficiently.
So we manage that complexity with a hierarchical, multi-agent framework. We break the task down into smaller, manageable pieces. How does that decomposition actually work?
We use different task decomposition methodologies to reduce the computational complexity, to shrink the search space. A really complex, long-horizon problem has a nearly infinite number of possible steps. By recursively dividing the task, we make the problem decidable, solvable by specialized agents.
Okay, so our sources detail 3 key ways to do this breakdown. Let's use an example. The high-level goal is to process a complex multi-stage insurance claim.
That's a great example. So first, you have hierarchical task networks, or HTNs. This is the very structured approach. The high-level task process claim is broken down using predefined methods until you get to basic primitive actions you can execute.
So HTNs are like a rigid, pre-approved flowchart.
Exactly. For the insurance claim, it might follow a very strict sequence. Verify policyholder identity, then calculate coverage amount, then route for medical review, then initiate payment. It's highly structured, deterministic. It's great for tasks where the process rarely changes.
Okay. Method 2 is functional decomposition. This breaks the problem down by required roles, not by a strict sequence.
Right. This divides the problem based on expertise. For that same insurance claim, you'd give a piece of the problem to an authenticator agent to verify identity, another piece to a calculator agent to determine the payout, and a third to a reporter agent to generate the regulatory paperwork.
So each agent works independently on its piece.
Right, which is great for parallel processing.
And the third method focuses more on the end result, not the specific steps.
That's the goal-oriented method. Here, agents are focused purely on achieving a specific desired world state, like claim status is finalized and payment status is initiated.
This sounds much more flexible.
It allows for the greatest flexibility. If the environment changes, say the primary payment API goes down, the agent can adapt its path. It might switch to a secondary EFT tool to reach the same end state, rather than just failing because one step in a fixed sequence was blocked.
Now, within this whole framework, you have the central conductor, the planning agent. This is the one doing the macro-level thinking, but not the actual work.
The planning agent is the general contractor. It orchestrates the whole flow, it interprets the high-level human intent, and it generates that adaptive plan using one of those decomposition methods. But it rarely, if ever, executes tools itself. Its job is coordination.
And the sources say it works through a kind of dual-layered abstraction to manage all this.
It does. There's the strategic layer, which is the high-level sequence identification. It figures out the what needs to be done. Then there's the operational layer, which details those components into precise executable subtasks, the how.
And those operational subtasks get handed off.
They get handed off to specialized executor agents based on their domain. The finance executor gets the initiate payment task, for example. And this hierarchical flow allows for massively parallel execution, which really boosts throughput.
So the agent swarm itself is highly specialized. Besides the planning agent, what are some of the other key roles we need for a robust enterprise setup?
Specialization is absolutely key for precision and avoiding that context overload we talked about. You have the executor agent, which is domain-specific and just runs commands.
The worker bee.
The worker bee. Then you have the vital verifier or critic agent. Its only job is to validate all output for safety, factuality, policy adherence, often using symbolic logic checking before any state change is executed.
And you need agents to monitor the system itself.
Yes, the monitoring or SRE agent, it just focuses on system health. It tracks latency, detects anomalies, triggers circuit breakers to prevent cascading failures. And finally, you have a synthesizer agent to aggregate all the outputs from the swarm and present a unified, coherent result to the user or the logging system.
That is a highly specialized team. So once you have this swarm of specialized agents, the critical architectural decision you have to make is how they all communicate and coordinate.
Right.
This is the classic distributed systems choice, orchestration versus choreography.
It's a fundamental decision.
Yeah.
And it dictates the trade-offs you're willing to make between visibility, scaling, and resilience. Architects have to choose. Do you centralize control, like a symphony conductor, which is orchestration?
Or do you distribute the logic, like traffic signals, which is choreography?
Exactly.
Okay, let's start with centralized orchestration, the conductor model.
In orchestration, a single master coordinator agent maintains the global state of the entire workflow. It explicitly dictates the action for each agent one by one. It waits for Agent A to finish its task, and only then does it tell Agent B what to do next.
The upside there seems pretty obvious. High visibility, lots of control.
Exactly. It's highly deterministic. The flow is predictable. It's easy to debug, easy to visualize. It's great for simpler workflows or ones that need a really strict, rigid sequence.
But the immediate downside I see is that single point of failure. And scalability must be a concern.
Absolutely. The orchestrator agent becomes a natural bottleneck. As your transaction volume grows, that coordinator service struggles to keep up. And worse, if that central coordinator crashes, the entire multi-agent workflow just grinds to a halt.
It's highly coupled.
Very high coupling. All the agents depend on that one central brain.
So for high scale, high resilience, or regulated environments like financial ledgers, the trend is shifting toward decentralized choreography.
Yes, the event-driven saga model. In choreography, there is no central brain. The workflow logic is distributed across the agents themselves.
So they don't talk to a central coordinator.
They don't. They listen for specific events that are emitted by other agents, and then they react.
Can you just walk us through a quick example of that decentralized flow?
Sure. Let's say the workflow starts. Agent A finishes its task and emits an event saying payment validated. Agent B, which is subscribed to that specific event type, picks up the message, does its local transaction, like log transaction in Ledger, and then emits its own event, Ledger updated.
And Agent C is listening for that second event.
Right. And it reacts accordingly, maybe by sending a confirmation email.
That just sounds inherently more robust and scalable.
It is. You get superior fault tolerance because there's no single point of failure. If Agent B temporarily goes down, the payment validated event just sits there, persistent in the message broker's log.
And when Agent B comes back online?
It can simply replay the sequence of events it missed, ensuring the system eventually reaches consistency without any human having to step in. The coupling is low, so agents can evolve independently.
So what's the big architectural trade-off? What's the cost of choosing choreography?
Global visibility becomes much, much harder. Tracking the overall status of a workflow requires complex distributed tracing to connect all those asynchronous events across multiple services. It demands a higher level of event-driven expertise, but for mission-critical systems where fault tolerance is the #1 priority, the resilience benefits almost always outweigh that complexity.
Okay, so regardless of whether we pick orchestration or choreography, the underlying plumbing has to ensure reliability. Specifically, durable execution and transactional integrity.
Absolutely.
What does durable execution mean in the context of these agentic workflows?
Durable execution is essentially the promise that your workflows are crash-proof. If the runtime environment fails, a power outage, a cloud service restart, whatever it is, the workflow has to be able to resume exactly where it left off.
Without losing state or creating inconsistent data.
Exactly. And that's achieved by modeling workflows as persistent state machines where every single action and decision is journaled.
Like a mandatory black box recorder for the agent's mind.
That's a great analogy. Every decision the agent makes, every tool response it gets, every policy check it passes is recorded in an append-only database.
So if the system restarts, it just replays the tape.
Precisely. It recovers by reading that journaled event history to reconstruct the agent's internal state, its goal, its current plan, its context. This eliminates that dangerous limbo state where a resource might be partially modified or locked, guaranteeing the workflow eventually gets to a defined end state, either success or confirmed failure.
Now, for the really high-stakes actions, especially financial or regulatory updates, data consistency is paramount. This is where we need atomic operations, patterns like two-phase commit.
Two-phase commit is essential for any action where you need an immediate rollback capability. It introduces a mandatory separation before the state change is finalized, which really mitigates risk. The process is broken into two non-reversible steps.
Okay, walk us through those steps.
First is the staging phase. The agent proposes changes and stages them in a reversible temporary format. Think of it like placing a lock on inventory or staging a reversible patch on a database table. Nothing is permanent yet.
And the second phase is the critical checkpoint.
That's the validation phase. Independent verifier agents, or maybe symbolic logic checkers in the trust plane, they scrutinize those staged changes against all the business invariants.
They check things like, does this violate any financial thresholds?
Or is the customer's PII still encrypted? Only after this validation and maybe mandatory human approval for high-risk moves are the changes actually committed to the production system. If any check fails, the changes are rolled back automatically, maintaining absolute transactional integrity.
This whole system seems to rely on the ability to retry failed operations without accidentally duplicating results, which brings us to maybe the most critical word in reliable distributed systems.
Yeah.
Idempotency.
Yeah.
Why is idempotency so essential for agentic reliability?
Because transient failures are a fact of life in distributed systems. They are guaranteed to happen. Imagine an agent tries to create a support ticket. The API successfully creates it, but the network connection drops before the agent gets the confirmation.
So the agent assumes it failed and tries again.
Right. And if that API call isn't idempotent, you now have two identical support tickets, which doubles the work and creates a mess.
So idempotency is crash-proofing the side effects.
It's making sure that running the operation once or running it 100 times results in the exact same state change. Every state-modifying tool and agent calls must be designed to handle retries safely.
How do you do that?
For write operations, like creating a new resource, the orchestrator should use a client-side idempotency key, a unique ID for the request. If the system gets the same key again, it knows it already processed that request and it just returns the previous result without doing the action again.
And what about for updates, not just creating new things?
For updates, you use deterministic mutations. So, for example, if an agent needs to change a case status from pending to approved, the logic should be only change the status to approved if the current state is still pending.
Right, so you don't overwrite a more recent change.
Exactly. If the status was already changed by another process, the update fails gracefully or just reports the current state. This rigor is what allows the orchestrator to aggressively retry transient failures, which is absolutely vital for high availability and data integrity.
Okay, we've established the plumbing. Now we have to address the core vulnerability, the inherent stochasticity of the LLM. How do you secure a system where the decision engine is fundamentally probabilistic? This is where safety and verification come in.
This is maybe the most challenging and, I think, the most innovative part of agentic architecture. To bridge that gap between the probabilistic model output and the rigid business protocols, we use what the sources call the decidability split.
Let's slow down on that term. Decidability split. What is that and why is it necessary?
The decidability split is the separation of the system into two distinct domains. You have the fuzzy creative reasoning of the LLM, and then you have the final, enforceable, deterministic decision logic.
So the LLM does the complex, open-ended problem solving.
But the final decision to actually act is not made by the LLM. It's made by a specialized symbolic checker that only operates on verifiable formal representations of the proposed action.
So the agent proposes, but a simple rules-based machine disposes.
Precisely. And this is formalized through a framework called actionable granular logic, or AGL. AGL forces the model's reasoning into an auditable knowledge state of explicit, discrete predicates and rules that guarantee algorithmic decidability.
What does that look like in practice?
Okay, so the agent proposes, I need to increase the resource allocation for Project X by 20%. That text proposal is then compiled into a formal representation, a set of logical statements.
And that formal representation gets checked.
It gets checked by a reasoning core that's restricted to what are called guarded profiles, which are logic fragments known to always yield a definitive yes, no, or abstain answer. There's no ambiguity. This guarantees the final decision core is subject to rigorous formal verification, and that mitigates the risk of a hallucination causing real-world damage.
That sounds computationally expensive. To make this verification efficient, especially at high volume, you'd need some kind of adaptive strategy.
And that leads to the Solve, Detect, Verify SDV pipeline. It's basically a triage system designed to balance accuracy against computational cost.
So you don't want to burn massive CPU cycles formally verifying that the agent correctly drafted a simple status email.
Exactly. So how it works is the primary agent solves the problem and generates the initial plan. Then, a lightweight detect module quickly scans the reasoning trace and identifies only the high-risk points.
Like financial transactions, data deletion attempts?
Or novel combinations of tools it hasn't seen before. It's just looking for red flags.
And the high-cost formal verification only happens on those red flags.
Correct. The robust verifier or critic agent is only deployed to validate the logic at those identified critical points. Verify. This avoids overthinking on simple tasks, and this is where you manage the concept of a verification budget.
So routine tasks get fast, simple verification.
While high-stakes reasoning, like a complex fraud detection algorithm, triggers a more deliberative, slow-thinking mode, which consumes more resources but guarantees much higher precision and safety.
Beyond the core logic, we also need these automated operational guardrails acting as checkpoints across the whole execution stack.
These are essential for enforcing least privilege principles outside the main reasoning loop. They operate at multiple layers. At the very beginning, you have input validation, screening incoming prompts for PII detection or unsafe content before the agent even sees it.
And a huge vulnerability right now in the LLM world is prompt injection. How do we defend against that?
Prompt injection defense is critical. You use techniques like system prompt isolation, making sure the core instructions are strictly separated from any user input. We also use semantic analysis to detect adversarial attempts to manipulate the agent or get it to reveal its instructions.
And at the critical moment of action, the API call itself is governed.
That's runtime permissioning and API gating. This ensures the agent is only granted the necessary tokens and permissions for that one specific discrete task at that exact moment in time.
So when it's done reading a document, its write permissions are immediately revoked.
Immediately.
Yeah.
And we also enforce output filtering for compliance, making sure the output adheres to expected schemas and doesn't contain any unauthorized data.
The level of rigor we're talking about here.
Right.
It means we have to treat these agents with the same security scrutiny as human employees, or maybe more accurately, as service accounts. It's a true zero-trust environment for AI.
Absolutely. The foundation of zero trust for autonomous AI is establishing a unique, verifiable agentic identity for every single participant registered in a central directory. This identity is the basis for all access governance.
So if an agent tries to do something, the system's first question is, who are you and what are you authorized to do right now?
Yes, and that identity enforces least privilege, so an agent can't just self-elevate its access. Furthermore, we implement contextual authorization.
So permissions aren't static.
No, they're dynamically adjusted based on the workflow context. An agent might have perpetual read access for analysis, but to perform a write operation like finalizing a purchase order, it might need a fresh, human-approved temporary token that expires the second the transaction is complete.
Protecting the actual secrets API keys, database credentials, that must be a huge security challenge, especially if the model itself is vulnerable to injection attacks.
That's handled through centralized credential management, and this is a non-negotiable security invariant. API keys, tokens, secrets are never directly accessible to the agent's reasoning logic or its context window.
So they're stored in a vault somewhere.
They're stored centrally in a secure vault and injected securely by the tool connector framework only at the point of execution. This prevents a successful prompt injection attack from being able to extract sensitive credentials.
And for the absolute highest sensitivity, like handling private financial records or national security data, we have to rely on specialized isolation tech.
That is confidential computing, which uses trusted execution environments, or TEEs. TEEs create a secure, isolated enclave for the agent that's protected even from the cloud provider's host operating system. And this provides two massive guarantees.
What are those guarantees?
First, logic confidentiality. The agent's reasoning, the prompts it's using, the sensitive data it's processing, all of it is protected inside the T. Second, attestation. The T provides cryptographic proof to an external auditor that a specific secure environment and a specific unaltered model were used for that transaction. It's the ultimate level of trust for highly regulated use cases.
All of this complex, highly governed activity, especially when it involves real state changes, requires ironclad proof of what happened. This is the whole purpose of auditing and observability, creating that immutable evidence trail.
It is.
And in mission-critical environments, traditional mutable text logs just aren't good enough anymore.
No, they're easily altered, they can be deleted, they're often incomplete. For mission-critical operations, we have to move toward deterministic observability and, crucially, trust in the integrity of the record. We need cryptographic audit trails using hash chains.
This sounds a lot like a blockchain approach, but applied internally to logs. How does the hash chaining work to guarantee integrity?
It's a mechanism borrowed from distributed ledger tech, yeah. We implement hash chain append-only logs. The mechanism is simple but incredibly robust. Every record written to the log includes the record itself and a cryptographic hash of the preceding record.
So if I try to change record 5, the hash stored in record 6 immediately becomes invalid and the change is obvious.
Exactly. Any attempt to alter a historical record instantly breaks the mathematical chain, and the alteration is immediately detectable by any auditor. And to ensure non-repudiation, every record is also digitally signed using the agent's private key.
So you have undeniable proof of which agent made which decision.
Right. And to prevent a bad actor from just rewriting the entire history from scratch.
How do you stop that?
That's handled by the immutability anchor. Periodically, the current head of the hash chain, the most recent validated hash, is anchored to an immutable external system. This could be a cloud storage service with write-once-read-many policies, or even a public distributed ledger. This external anchor prevents the entire history from being rewritten. It locks the data.
Beyond just the integrity, the audit trail needs to provide context for a regulator or a forensic team. Just capturing the outcome isn't enough. We need multidimensional traceability.
We have to capture the decision logic that led to the action. This means capturing 3 distinct log streams for every single operation.
Okay, first is the internal thinking.
The reasoning trace. This log captures the model's thought steps, its analysis, its alternative considerations, its confidence scores. This is crucial for explaining the why behind an agent's sometimes non-intuitive behavior.
Second, the actual execution.
The tool execution log. This captures the raw API endpoint, the parameters that were passed, the time it took, and the exact response it got back. This is the verifiable proof of the interaction.
And third, the compliance check.
The policy evaluation log. This captures which business rules were checked by the trust plane, the outcome of that check, and whether any guardrail blocked or modified the execution. If a human had to step in, the identity of the approver and the timestamp are logged too. This comprehensive data set is what turns the opaque process of AI decision-making into a transparent, verifiable chain of custody.
Okay, so once all this highly governed architecture is in place, the planes, the durable plumbing, the crypto logs, the operational challenge is still there.
Yeah.
How do you move this from a controlled sandbox into live production? You can't just flip a switch to full autonomy.
You absolutely cannot. Stakeholder trust, both internal and external, has to be built gradually, and you do that through the phased rollout framework. This framework systematically increases autonomy based on demonstrated performance and rigorous data-driven verification.
Walk us through those phases. How do you move between them?
You start in shadow mode. The agent operates completely in a non-production environment, running its workflow in parallel with human experts or the current system. It makes recommendations, and its outcomes are compared against the human baseline.
So you're just identifying logic gaps and performance issues without any real business risk.
Exactly. The KPI here is just achieving parity with human performance and finding failure modes.
Once that baseline is good, it moves into production, but under strict supervision.
That's advisory mode, or human in the loop. The agent is deployed in the live environment, but every single proposed state change requires explicit human approval. This builds essential trust with your end users, and it makes sure the system can handle real-world edge cases correctly. The agent is learning on live data, but the human has the final veto.
And the goal is to get the human to only monitor the high-risk stuff, which happens in the next phase.
Limited autonomy. Based on the performance data from advisory mode, the agent gets permission to execute low-risk, high-frequency actions automatically. For instance, processing a small refund under a predefined dollar amount. But complex, high-value, or novel cases are still automatically routed to human experts for mandatory approval.
So it's delivering real value now, but with risk ceilings.
Predefined risk ceilings, yes. And finally, you get to the target state.
Full agentic execution.
After a sustained, measurable period of error-free operation and compliance in the limited autonomy phase, the system manages routine incidents from end to end. Human experts are only pulled in when there's ambiguity or a predefined risk threshold is crossed,
Like a massive spike in transaction volume.
or a regulatory change. The human role shifts entirely from execution to strategic oversight.
And this shift requires a specialized operational support team. We're now talking about the need for agentic site reliability engineering, or AI SRE.
AI SRE is a new specialized practice. It's focused on reducing the operational toil of monitoring and troubleshooting these agent swarms. Because the systems are so complex, you've got LLMs, tool frameworks, message brokers. Persistent storage diagnosing a failure is incredibly difficult for a human SRE.
And this is where the meta-governance comes in, using agents to fix other agents.
It's the most innovative concept here, I think. Using AI SRE agents themselves to monitor, investigate, and even remediate incidents in production. These specialized agents can triage noisy alerts, correlate all those distributed trace logs from the data and trust planes, isolate the root cause of a failure.
And even draft the initial summary of what went wrong.
All within minutes, far faster than a human team ever could. This dramatically reduces human operational toil and improves the mean time to recovery.
And finally, we have to acknowledge that unlike traditional software, these agents are subject to model drift. The environment, the data, the models themselves, they're all constantly changing.
This dynamism requires explicit architectural controls. You have to establish a regular retraining cadence based on drift detection signals. Critically, you need rigorous version control for prompts and tools. If a new prompt template causes unexpected behavior, you have to be able to roll back to a stable version state instantly, just like a software release.
And you have to keep testing it.
You need continuous red teaming, ongoing stress testing specifically designed to find emerging vulnerabilities, like new prompt injection techniques or unexpected risks in how the agents coordinate before they cause a catastrophic failure.
This has truly been a monumental deep dive into what it takes to build a trustworthy, reliable, autonomous system. We started by acknowledging that AI has moved definitively from being a passive information tool to an autonomous execution engine.
An engine performing real state changes. And that shift is not an application problem. It's a rigorous systems engineering requirement. To manage the inherent unpredictability of the models, the architecture has to impose structure, governance, security, and verification.
We saw that realized through the mandated separation of the control plane for defining policy, the data plane for stateful execution,
and the critical trust plane for independent, real-time verification and accountability.
We really emphasized that every autonomous move must be durable through techniques like idempotency, state journaling, two-phase commits, and it must be verifiable. We discussed how rigorous methods like actionable granular logic and the adaptive solve detect verify pipeline are required to bridge that gap between probabilistic thinking and deterministic business compliance.
And by understanding concepts like idempotent operations or the rigor of cryptographic audit chains or the purpose of contextual authorization, you are no longer viewing AI as some kind of magic. You're seeing it as a highly complex engineered system.
Right.
This deep dive gives you the crucial insight you need to evaluate the success, the safety, and the regulatory compliance of any new enterprise automation initiative. It transitions you from being a consumer of AI technology to an architect of enterprise autonomy.
The ultimate goal, as the source material suggests, is to liberate human experts from routine, high-toil tasks so they can focus on what they do best: strategic decision-making and judgment.
Which leads us to our final provocative thought for you. If this elaborate framework is so successful that AI SRE agents are now capable of monitoring, investigating, and even remediating failures within the autonomous systems themselves, does the ultimate human role in the loop, the highest level of strategic oversight, boil down entirely and solely to defining the initial policy and the highest level ethical boundaries? Something to mull over until our next deep dive.